We'll scroll to your answer in a little bit, but first we'll walk through what this is saying. So if we're going to do an electrophile addition of H plus from HCl, this is actually going to be kind of interesting to go through and do because I don't know how they're presenting it down there, but the words mean one thing, so we'll show what the words do. So for step one, what it sounds to me like they're doing is they're saying H plus. Okay, so if we're going to do an electrophile addition of H plus, okay, the most reactive thing here being what? What's the most reactive thing we see? In this reactions. Right now there's two reactants. We have the cyclohexene and we have H plus. What's the most reactive? H plus. So what do we need to do to fix H plus? Why is H plus reactive?
It's got no electrons.
It's missing electrons, so we've got to find electrons. Where are their electrons? In the pi bond, also in a lot of different sigma bonds. So the question becomes, which of those is the most highest energy source of electrons? And yes, now it's the pi bond. Why is the pi bond highest in energy? We're using the p orbitals, which are higher in energy than our s orbitals. So what we would do is show our electrons. Whoops, that was horribly drawn over. We'd be looking at our pi bond, taking electrons out, and sharing it with the hydrogen. We don't change any of the rest of the structure. Okay, and now we would need to show our bond between a carbon and a hydrogen. Which carbon should the hydrogen be bonded to? Which is somewhat intentionally a really tricky question. At this stage, can you tell a difference between any of those carbons? No. So it's very tricky, so let's clean it up a little bit. Okay. We'll have it a blue carbon and a green carbon, because that's where our pi bonds were originally located. So now, where should the hydrogen be, blue or green carbon? Still equally challenging. There is no difference between the blue and the green carbon, so ultimately that means doesn't matter. You can attach that hydrogen to either one and it's not going to have an effect, or it should not have an effect on the overall answer. Whether it does or not is a separate issue, okay, but it should not have an effect. I'm going to go ahead and show it on the green one. I'll put the hydrogen there. Have I now drawn the correct answer? What's wrong with it, Caden?
You need the charge on the blue.
Okay, that blue carbon has lost electrons because it gave up the electrons to make the bond between the green and the hydrogen. Because it has now lost electrons, it should be positively charged. And it looks like there was a little carryover from my hand. Okay, that's now your electrophile addition addition of HCl from, try that again, of H plus from HCl. There is another possibility that what they drew was H bond Cl. Okay, and again, I don't know, is that what they actually drew? Yeah. So our electrons are coming down to pick up the hydrogen, but now we've formed that extra bond to our hydrogen. Hydrogen's exceeded its octet. We should have a second arrow breaking those, and we would have our Cl chilling off next to it. This does introduce a potential issue within SmartWork. Depending on what they're asking you to draw, you may or may not need to include the Cl. So you've got to look at the instructions for that individual box to make sure you know what you're supposed to be including. I'm assuming it's a 2-box reaction, which means you'll need to draw the Cl, because to do the next coordination, you'd need the Cl present. Okay? So if we're now looking at those products, what's the most reactive thing you see?
Cl.
Why is the Cl reactive?
It's not neutral.
Cool. What charge does it have?
Negative.
How do we stabilize it?
Positive.
Do I have a positive?
You do.
So what should I do?
Connect them.
What happens to the charge on the carbon?
Neutralize.
What happens to the charge of the chlorine?
Neutralize.
Neutralize. Do I need to show the hydrogen anymore?
Nah, it's implied.
It's implied, so we can get away without showing it. Okay, this becomes one of the reasons why this type of reaction, addition reactions, can become challenging, particularly within smart work, because we try to go through and say, well, what things were added? And if we said what things were added, it was a hydrogen and a chlorine across that pi bond. Smart work gets tripped up by this, okay, and this is a grading issue. Once you've identified a hydrogen on a position, you either need to identify the charge or you have to show all implied hydrogens at that position, which is a problem even back with our first intermediate. Okay? So either imply always or don't imply. Make sense?
Yeah.
Okay. So now the question, is this an issue within smart work? Did you draw all that?
I just didn't draw the additional hydrogens, but everything else I did right.
I would bet it's that additional hydrogen, because without that additional hydrogen, smart work is saying you're now not implying hydrogens because you've shown one. So they look at it and say you're showing a 3-bonded carbon without a charge. This is a problem. So I would argue that's a grading artifact. In this case, I didn't see how many attempts you had there, but yeah, it's probably not going to affect your grade. If you're concerned about it, you can send me an email and I can fix it. So if we go through and show or look at what they showed, you'll know they aren't showing the hydrogen at all because they decided to imply it all the way through, which is fine. Make sense? I will say that in hand-drawn work, I won't complain about that implied hydrogen, not or partially implied and partially not implied. I might circle it and write SW5 next to it, just so that you're aware that that could be an issue in the online homework, but that's it. I wouldn't take off points for it. Make sense? Questions?
I can go in and do another attempt and it'll be fine.
Yeah, you should be able to go through and do that attempt. You can look at your total score and see if it's worth me going in and adding a point. It's probably not going to affect your grade enough to worry about, but I have no objections to doing so.
Thank you.
Next question. I mean, we can kind of cheat. Yeah, it doesn't affect your grade at all.
Chapter 8, question 3.
So we're looking at energy diagram, and the way it's formatted is in such a way that it could apply to either an SN1 or an E1 reaction. So what they're trying to get you to do is to think about how those mechanisms are slightly different and ultimately how their energy diagrams are going to be slightly different. So within that system, what I would do is draw out a generic mechanism where I can see the split between SN1 and E1. Okay? Which theoretically shouldn't be challenging because it's literally done for you in the notes where I've done that. Okay, so we can see that split. If we're starting out with our material, we've got a leaving group connected to our substrate. Okay, if we're going to sort of color code this, if I remember my old color codes. We've got our substrate. That substrate in a one-type mechanism is going to do what? Okay. So we talked about it a little bit in the lab, and I said this is something that you need to reflex into, and it becomes very important as we navigate more through these particular reactions. When I say SN1, you're supposed to say?
I took 2.
I'll get to 2 in a second. What did you say?
I didn't say.
You didn't say?
Carbocation.
Carbocation. Right? If I said SN2, you're supposed to say?
Backside attack.
Okay. In this case, the backside attack, good thing you memorized, that was not particularly relevant here. When we say SN1, the most thing we're concerned about is carbocation. Okay? Pushing that on SN1 and SN2 is important, but it's less pushing SN1 and SN2. It's pushing 1 versus 2. The 1-type mechanism is going to form a carbocation. The 2-type mechanism, we're concerned about backside attack. When we move into the E2, it gets a little bit gray area, but it's still technically a backside attack. Right? So if you remember 1 and 2 as carbocation and backside attack, that can help us out. Because if we're going to say SN1 or E1, these are both one-type mechanisms. I want to form a carbocation. So the very first thing I want to do in my chemical reaction is do whatever I've got to do to make a carbocation. Okay, well, what do I need to do to make that carbocation? The leaving group needs to leave. Okay? That wording becomes important. You'll see me be persistent and obnoxious about that even through second semester. When you say something leaves, you are saying it takes the electrons with it. Okay, that is part of that statement. So if we're going to say a leaving group, what we're saying is the electrons in that bond go to the leaving group. The leaving group has now picked up a pair of electrons. In most of the scenarios we're looking at, the leaving group carries a negative charge. That is not always the case because the leaving group could be positive to start with. Okay? So we've got to be a little bit careful about just assuming it's always negative. The most important thing is that it has that extra lone pair. Oops, drew that kind of small. And then we formed our carbocation. The carbocation is going to become important because when we're running these mechanisms, that is going to be an artifact of all of them. Okay, we now have a carbocation. Now what could we do to that carbocation? Said another way, is the carbocation stable?
No.
No. So what do we need to do? Stabilize it. How do you stabilize the positive charge?
Electrons.
With a negative charge-ish, where I'd rather go is with electrons. Okay? So we now have to look for those electrons somewhere else. Okay? This is where we encounter the branch point in our potential mechanisms. Okay? If we add a nucleophile, that nucleophile is supplying the electrons to our carbocation. And we've now made that new bond between the nucleophile and our substrate. If instead we add a base, that base comes in, removes the hydrogen as H+, and our electrons can swing in. This is dropping multiple colors on the same thing. That's problematic. Or multiple arrows. And we get the double bond. So with that positive charge, there's multiple ways we can stabilize it. Deciding what way stabilizes it is going to depend largely on what that reagent is, that secondary reagent. Is it acting primarily as a base or as a nucleophile? What you're hoping for is some piece of information to tip the scales one way or another. As you probably noted in the videos last week, the difference between a nucleophile and base is very, very subtle. So one of the complications we'll find for the SN1 mechanism is that it's always competing with the E1 mechanism. Okay, so we have to be aware of that always being a potential issue. So if we're now looking at our reaction kind of all the way through, what happened? We have our substrate starting at a relative ground state. That substrate's going to apply to A, our reactants. The very end of this E is going to be our products. And then because we have two steps, this is 1 and 2, I'm drawing that 2 awfully close to just the substitution. Okay, so this is step 1 and step 2. Those would be our transitions through there. Okay, what we're getting in C is our carbocation. So what they're trying to get you to do is see the differences between these. Okay? If we look, are the reactants the same for both of these mechanisms?
No. A little different.
Okay, so if we, I don't know there's an easy way to do this, but I'm going to try it. Okay, we look at just the SN1 mechanism. Okay, so we just think about that. And then we go through and we just think about the E1 mechanism. What's the only thing getting erased? So there's E1. Nope, that didn't do what I wanted it to do. There's E1. There's SN1. What's the thing that's getting erased in both those cases?
D.
The last part, okay, where we're splitting away from the carbocation. So if we're going to go through and answer the question, which species are the same for each type of reaction? Well, the reactants, are they the same? Yeah. How about C? C being our carbocation. We have the same carbocation in both cases.
Yeah.
Yeah. Okay, which then means B, the intermediate on transitioning from A to C, is also going to be the same. Okay? What's going to be different, it's what's happening in that second step. That second step was our transition state D forming into our products. Are the products different?
Yeah.
Yeah. So what we're really trying to go through and note is that when we look at the SN1 and E1, this part of the diagram is identical. When we look at the second part, we're now going to see a difference between our SN1 and our E1. Where are we going to see that difference?
You mean like at D starting or 2?
Okay. So if we were going to predict, looking at an energy diagram for each of these reactions, how would we expect D and E to vary?
I think SN1 would like have the product send at a higher energy because it's endo equivalent.
Okay? And SN1, our product should end at a higher energy state. What do you guys think? What's higher in energy about this black nucleophile structure versus our blue-green leaving group structure, our substrate? Anybody see any obvious differences?
We have less electrons. Yeah, never mind.
We got the exact same number of electrons.
One's black and blue.
Okay, so let's try the other way. Our blue-purple structure versus our elimination product.
Yeah, different shape. And one's pi bond and
Push on that. There's a pi bond. Is the pi bond a different energy than my sigma bonds?
Yeah.
Yes, which means what would happen to the energy of my product for the elimination?
Higher.
It should go higher. So more than likely, the elimination is actually going to have higher energy products than our substitution. So flipping it. Okay? And if it hasn't sunk in with you yet, right, if we're talking through a lot of these answer choices that people are putting out there, they're hinging on a 50-50. It's either higher or lower. Yes, it's one of them. And if we stack a bunch of higher, lower questions together, they're easy 50-50 questions, but the instant you get one wrong, the whole triage of 50-50 questions falls apart. Okay? So a very subtle change to how you're thinking through things can make you go from, oh, I know everything, to being non-existent in the content. Okay? So you have to be very, very careful to really understand each of those pieces. Kind of make sense? Okay. And because it was specifically asked about this question, we'll scroll through to go ahead and look at their answers so that way we can ensure we aren't doing anything misleading. So the same for SN1 and E1. As we went through and said, it was the first half. That was our ABC. And then the difference, D and E. Okay? I want to push on that difference, D and E. Okay? Let's think about that. If we talked through this, okay, let's get rid of our E, based off of kind of our initial assessment of those structures, okay, we would expect the SN to be a little bit lower in energy than our elimination. How much of an effect is that going to be on D? Okay? Because what we're saying is to transition from C either to our elimination product or to our SN product is going to be different because the energies of those products are different. How much is that going to change the energy of D? That's a very hard question for the record. Why would you predict it to be lower for the SN?
Just because of how much lower, like the SN
Okay? If SN's lower, shouldn't that one be lower? Yes. How significant is that drop? That's the real question, is the significance of it. How much of a difference would we expect there? This is a tough question, and it's one that was addressed by Hammond through what is known as the Hammond postulate. Okay? Which I remember always thinking it was dumb. Why would anybody talk about it? And this is the specific case of why someone would talk about it. What the Hammond postulate is saying is that our transition state energy, okay, is dictated mostly based off of the species it is closest to. And by species, we're looking at that particular transition state. We're talking about the reactant and product of that individual species. And this particular energy diagram, where is the transition state closest to? The reactants or the products? The reactants. And if the reactants are the same energy, what does that suggest about the transition state? It'll be roughly the same energy. So even though there's a large shift in the product energies, that's not much of an effect because the transition state is dictated as closer in energy to the reactants. Okay? It's a really kind of nuanced thing, and it's not that big of a deal to forget, okay, or ultimately not worry about. But because I recognize my own personal mistakes, I try to point out those potential issues and why it's actually kind of important. Okay?
So is this how most reactions are going to look? As far as like, because obviously most of them we've been seeing just kind of have one sort of like one S versus has like, you know, two little camelback pumps on it.
Ask your question again.
I said, this is how most reactions are going to look as far as like having two camelback little humps on top.
No. So what I think you're saying is that if we're looking at an individual reaction, would we expect our reactions to have two humps?
Yeah, isn't it just that like that because of the carbocations being C?
Does this reaction have two humps? No, it only has one. So the classification, are most reactions going to have two humps? I think you're trying to pigeonhole things too much. Okay? The amount of humps that you have within it are dictated based off of the amount of mechanistic steps that are in your individual chemical reaction. Okay? I will say for the most part, this semester, we're limited to 3 to 4 mechanistic steps. And that's usually the high end. If we move into second semester, there's a couple reactions towards the end that push 10 to 12 mechanistic steps. Okay? There was a lab that I really liked, but the lab never really worked, and it was mostly just an exercise on drawing out mechanisms. And that mechanism pushed, I think, 23 steps. Okay? When you're looking at 23 steps, is it really valuable to draw out an energy diagram for that? No. What we're using the energy diagrams to do is to discuss relatively simple, short reactions. So your energy diagrams are usually going to cap out about 4 steps at most. And I can really only think of one case where that is, because I'm really trying to reinforce that differential between what we see within a mechanism and what we see with the energy diagrams. For the most part, you're going to be in 1 to 2 steps. So you want to call it 1 camel hump versus 2? Yeah. That's going to be your standard existence. Okay? But saying all reactions are that is no. Make sense?
Right.
Don't be freaking out about 23 steps now. That's like 6 months away. Okay? Worry about the next 6 weeks. It's even less than 6 weeks.
I was gonna say,
Yeah. Okay? Make sense? Everybody good with it?
yeah.
Okay. Next.
Question number 2,
It's a grouped question, so I will actually go to yours. apparently I went to the wrong one. You said chapter 8, right?
Yeah.
Oh, I bet you I clicked the wrong U. Yep. Okay. So in chapter 8, one of the big differences that you get in chapter 8 versus chapter 7 is that, actually, they tell you what mechanisms. Theoretically, you're supposed to be able to look at a reaction and to decide what mechanism is going on within it. Okay, we limit things a little bit by saying we're looking at substitution or elimination as chemical reactions. So that's supposed to help out. So if we were to go through and look at this, how would we know whether we were doing a substitution or elimination?
E1.
What's that?
The E1 suggests elimination.
So how do you know it's E1? Yeah, I know why you were. Okay, so this is where we would have to be careful and try and process through all of our information for deciding individual mechanisms, okay, what style or which one we should be looking at. You should be considering your substrate. You should be considering your nucleophile or base. You should be considering any secondary pieces of information like reaction conditions to help push one mechanism for another. Okay? In this particular scenario, we've got a secondary substrate. So we look at where our leaving group is located. Bromine being our halogen is a good leaving group because it can withdraw the electrons from our carbon. So we go back, look at that carbon. That carbon is connected to two other carbons, so it's a secondary substrate. Secondary substrates, unfortunately, favor what or are allowed in which mechanism? All the mechanisms, okay, or all the reactions. So looking at the substrate doesn't help us. We could then move to looking at the nucleophile and or base. This one becomes a little bit more tricky to evaluate because when we go through and look at that, can we tell whether it's a nucleophile or a base? Okay, I'm going to take silence to mean like I don't know what we're talking about, okay?
Yeah.
What if we drew out the Lewis structure? Does that look like the proper Lewis structure?
Yeah.
We're missing a lone pair. The nitrogen should have an octet. And if we actually paid attention to how we were supposed to draw out the Lewis structure, we'd realize that our drawing is short 2 electrons. That nitrogen should have a lone pair of electrons. That lone pair of electrons should now at least set up the system that we could be looking at a nucleophile or a base because we have an electron source. Is this a strong nucleophile or a weak nucleophile? / base. Why weak?
Well, there's no charge.
There's no charge, which then means we're sitting in the SN1 or E1 category. Okay? So we've eliminated SN2, we've eliminated E2 as possible choices. We're now stuck between SN1 and E1, and now we do have a genuine issue here because how do we differentiate between those two?
Wait, hold on, let's go back to it again, because there was only those two because not having charge?
Yep, because this is a weak nucleophile / base. To get SN2 or E2, you need a strong nucleophile or base. Since this is weak, it's not SN2 or E2. So we could eliminate those from our choices. We'd now be stuck in this gray area between SN1 or E1. And how would we go through and decide? Okay? That decision is ultimately going to come down to the framing of the question. If it's multiple choice, look at your answer choices. What do you hope to see in your answer choices? 4 answers that have double bonds, or 4 answers that do not. Because if there are 4 answers that do not have double bonds, what was the mechanism? Substitution. If there are 4 answers with double bonds, elimination. What if you see some answers with multiple bond or double bonds and some with all single bonds? Yeah, now you're kind of stuck in a gray area, and that's when you should be looking for the answer choice multiple or true, okay? Because you're being able to differentiate is challenging, right? Ideally, the question would add a little bit more context, like a temperature. Let's say 25 degrees Celsius. What is 25 degrees Celsius?
Room temperature.
Room temperature. And if it's room temperature, what does that mean you're not doing? You're not heating. And if you're not heating, that favors the substitution. If we looked at it and it instead said 60 degrees Celsius, now we're adding heat, that would suggest that we're looking for the elimination. Okay? In this case, it did not specify a temperature. So how would we go through and do it? Well, we would go through and actually look at the part of the question that I erased, and it says that we're doing an E1 reaction, okay? Which means we need to be doing our elimination. So in this particular case, they're asking for the intermediate and the major organic products, so we have to stack to two potential reactions. Okay? First step in our mechanism is what? When I say one type, you say, let's try it again. When I say SN1, you say carbocation. When I say one type, you say, it's the same thing. Carbocation. There we go. Okay? Because that one type is now going to trigger carbocations, whether it's SN1 or E1, it's still the same process, which means the first step of our reaction needs to be create a carbocation. So add an arrow. In this case, they're just asking for intermediates and products. We don't have to add arrows, but the arrows provide the instructions that allow us to understand what's going on. We could go through, have the elimination happen. Okay? We could go through and show that hydrogen, and we would have our carbocation there. We would also have Br minus chilling out. And since I already had that hand action, we'll put it there. Okay? The hydrogen was wedged. Why am I not showing it wedged anymore? It's position change. That kind of confuses me a little bit because it's connected to the same carbon. What's that? There's an interesting statement. Yeah, when the bromine was there, okay, the electrons in that bond to the bromine forced the hydrogen up and out. Okay, since the bromine's not there, it's not forced up and out, it's forced into the plane. Said another way is what I believe Abby said. It's not chiral anymore. This has 3 groups of electrons. This has 4 groups. 4 groups is tetrahedral. That's when we need to show our wedges and dashes. This is not tetrahedral anymore. I don't need to show wedges and dashes. Okay? So 2 different talks, same eventual answer. I kind of like Adolfo's approach a little bit better, a little more scientifically rigorous, but it's the same process either way. Okay? So this would be our intermediate. Deciding which of those you should draw in the box, I would bet you're only supposed to draw the carbocation and you're supposed to leave the bromide off. Again, I could be wrong. We'll dig into that in a second. Okay? The last part, we have to move into our second step. In our second step, we're now focused on actually doing the elimination. Okay? In the elimination process, we need to have our base come into play. The base in this case is going to be the NH3 with that lone pair of electrons. That NH3 needs to remove a hydrogen. Okay? What hydrogen does it remove?
That one that says hydrogen, the most common, I guess. Less than that.
Okay? So there's lots of different answers in this, and we're going to push on it in a second. Okay? One statement is just let's pull off the hydrogen that we see, because there's a hydrogen there. Okay? If we do this, what happens? That base shares the electrons with the hydrogen, so we're going to get NH4 plus. Okay. That hydrogen had a bond to the carbon, right? What happened to that bond? Went to our carbon. Okay. The resulting structure would look something like this, which is really, really, really misleading. I would argue it's a little bit better if we show the lone pair, but even then, it's still pretty misleading. How many bonds does that carbon have? 2. Not 3, because 3 would mean there's an implied hydrogen. Is there an implied hydrogen there? No, you got rid of the bromine. There was only one hydrogen there, and that's the one you just deleted.
Yeah.
Okay? So why is this particular structure problematic? That carbon is missing its octet. Okay? That's a really big issue, and there's no way to fix that. Okay? So that structure is insanely unstable and will immediately reach out, pull the hydrogen back from the NH3, sending us into the reverse direction, which ultimately means, to Adolfo's suggestion, let's pull the hydrogen that's obvious, that's standing right there. That one is going to be wrong because it results in a very unstable intermediate structure. Okay? One of the statements that Adolfo also said, which was good, I actually liked that statement, still technically wrong, but good, the most common. Is that hydrogen the most common hydrogen in that molecule?
No.
No, if we think about common, we're probably talking about the amount. There's 3 hydrogens out here. There's 2 hydrogens here. And there's 3 hydrogens out here. If anything, the hydrogen that you wanted to attack was the least common. Okay, not only was it the least common, it resulted in the least stable structure. Okay, and if we push on this further, this said it was what kind of a reaction? E. What does the E stand for? Elimination. How do you know you have an elimination? You had to form a pi bond. Did we form a pi bond? No. This is where I will get some people being, but well, Mike, you were just being stupid about it. You should have moved the electrons into the double bond there. And to that statement, I would say, what did you do to those blue hydrogens? Nothing, which means you've broken the octet.
So, couldn't you see that? Couldn't you take one of those hydrogens now that you have one?
Ah, okay. So now we say the black hydrogen didn't make sense. Everything about it was screaming bad. There was nothing we can do to fix it. So instead, let's have our base remove a blue hydrogen. Okay? After all, that blue hydrogen is closer, is it not? It's the problem with proximity. Are we now married? No. Okay, so it's not about proximity. The proximity is wherever you chose to draw things. Don't base your reactions based off of proximity. Base it based off of something else. That something else is going to become important here. If we take the electrons in that bond, where do we want to put the electrons in the bond between the carbon and the hydrogen? 2 very good answers. Okay, I accept that answer. I don't want to draw that answer yet. When we had the base come in and remove the black hydrogen, where did we put the electrons?
Back in the carbon.
On the carbon. So what's a good place to do here?
Back in the carbon.
Put it on the carbon. Okay, so we could take those electrons and drop them onto the carbon. What would the resulting structure look like? Did nothing to the carbocation. That's a very sloppy carbocation. Slightly better. And we'd now have that lone pair of electrons. If we wanted to get fancy, we could draw on those 2 hydrogens. Is this a good product? Why not? There's lots of charge, but what could you do? Move the electrons down through a process known as resonance. Okay? If we're now considering mechanisms, is this a good mechanism to do? It's not horrible. I will 100% accept this as a mechanism. Okay, smart work is going to get a bit irritated at you. Okay, and some instructors would get irritated at you. It's a problematic mechanism because the arrows you drew resulted in an unstable structure. When we draw mechanisms, our goal is to always draw the most stable product we can possibly draw within our allowed arrow pushing moves. And how could we move the electrons from that bond? Well, we could move them from a bond to an atom, or we could have moved them bond to bond. That bond to bond arrow pushing takes you immediately to that product. Make sense?
Yeah.
Have you done an elimination?
Yes.
Yes. So this could be a step up over the black one. Okay? But if you enter this into smart work, you're wrong. Okay, why?
It's not stable, or as stable as it could be.
There's a better statement. It's not as stable as it could be. What do you mean?
Well, E1 allows for cis and trans is the most stable.
This doesn't have cis-trans isomerism, so while your statement is true, it's irrelevant to this particular drawing. When we started this step of the reaction, what did we try to find? Finding a good hydrogen to do what with?
Leave.
What did leave mean? Take the electrons. The hydrogen's not taking electrons, a good hydrogen to remove. We started with the black hydrogen and we said that was a bad choice because it resulted in a bad structure. We then tried the blue hydrogen and it resulted in a good structure. Does that mean the orange hydrogen and the red hydrogen are now also bad?
No.
You didn't look at them, so who knows? What should you do?
Try them all out.
Okay? You should try them all out so that you're used to the process behind how that functions. Once you're used to that process, you won't have to draw them all out because you'll be like, oh, that one doesn't make sense. For instance, if I went after the red hydrogen, what happens? I could take those electrons, and now where do I put the electrons from that hydrogen-carbon bond? Okay, carbon. Why do I not take them to the bond?
Oh. 'Cause you have to.
If I tried to take them to the bond, I would exceed the octet at that position. So the removal of that hydrogen, the red hydrogen, is too far away to do anything to stabilize with the carbocation. So there's a distance issue that comes into play here. So that red hydrogen maneuver ultimately results in a structure that's very unstable, and there's no resonance options to be able to stabilize it. So I'm going to erase the red one. What about the orange one?
Yeah, it'll work.
Now we're in a proximity right next door where we could take the electrons from our base, remove the hydrogen, the electrons in the carbon-hydrogen bond, now go to the bond, and what's the resulting structure? Okay, so now we have this issue. The orange structure, to Ivan's point, now has the ability to do cis and trans. Okay? How do I know which one it does? Does it give me cis or does it give me trans?
Trans.
Whoops, I need to draw it the other way so it fits. Why should it give me trans over cis? Ivan?
Trans is more stable.
Trans is more stable than cis. You're taking the electrons in those bonds and you've put them on opposite sides as opposed to the same side. You're getting effectively an electron repulsion. So trans is more stable than cis. This does potentially introduce an issue when you move into E2 because E2 isn't necessarily going to favor cis or trans. It's going to produce the one that the stereochemistry allows. Why do I not have to worry about stereochemistry in this particular scenario? It has nothing to do with it not asking it. It has everything to do with the fact that we actually already answered that question. When we look at the formation of the pi bond, do I have stereochemistry? Do you see wedges and dashes?
No.
No. Remember, the carbocation removed the stereochemical issue. Okay? Which means I don't have to worry about stereochemistry. I'm going to remove the hydrogen that produces the more stable double bond. So between the cis and the trans is a better product, and I can eliminate the cis as a possibility. Does it still form? Yes, in smaller amounts, because there's an electron repulsion that minimizes the likelihood of that happening. So the trans is more favored. But between the blue and the orange, which one's more favored? Why is the orange more favored? It's more stable. Okay, use a different S word. Careful with your choices. More than 4 letters. More substituted. The orange has 2 substituents on it. The blue only has 1 non-hydrogen substituent. That makes the orange pi bond more stable than the blue. I would favor the orange product in this. If we think through the elimination reactions that are initially talked about, when we run those reactions, there's no difference between the hydrogens we remove because the starting material was symmetric. Is our starting material symmetric here? No. And as soon as you introduce asymmetry into your starting materials, you're going to get asymmetry into the products. You have to be aware of that when manipulating these particular reactions. Okay? Would argue that has now answered your question, but well, I'll check. Are you okay with that, Carly?
Yeah.
Okay. One more thing I do want to push on. When we looked at this reaction, black and red did not work. Blue and orange did work. What did blue and orange have in common? What's that? True, they both allowed for the formation of the pi bond, but you're really only answering that because we can see the products. So what do we see in the reactants that's similar between orange and blue that would allow me to keep my focus at orange and blue and not have to look at black and red? There's no resonance.
They're closer to the carbon cation.
They're closer than red. They're not closer than black. Black's even closer to the carbocation.
So something to do with charge?
No.
Question?
Okay. As a potential hit, proximity is now going to be an issue. So I like where you're going with that. You just went too far. They aren't super close. Black is super close. Orange and blue are a little bit further away. So you could say the orange and blue were one carbon further away from the carbocation. That works. Okay, that's a lot of words. Scientists don't like words, so we try to come up with a numbering system for it. If the carbocation is where my chemistry is located, I could call that position alpha, the first in the chain of my chemical reactivity. Since the black hydrogen is located at position alpha, it can't react. But one carbon further away can react. And if where my chemistry was here was alpha, one carbon further away would be beta. And because this is a branch, it can go two different directions. That means I have two beta positions. One of the other names you'll hear floated out there when talking about elimination reactions is beta elimination. Why are they saying beta?
That's what they want to eliminate right now.
Okay. They're referencing the position where the hydrogen needs to be removed. Okay. Subtle aspect within the nomenclature behind it. Arguably, it's a bit of a BS system, but it's there. Kind of make sense? Okay. Questions about what's up there? Okay, we'll delete that. Let's see, did it give me the solution? So there's the carbocation. They didn't show the hydrogen. They didn't have to show the hydrogen. Okay, again, we could imply that. Note what they didn't show was was it bromide? Yeah, they didn't show the bromide. They say in the directions very clearly only show the organic materials. So make sure you look for those pieces. And then part 2, draw the major organic product. They're showing the trans product as they correctly should. Okay, if you drew the cis, they might actually give you credit for it, but they would say this is technically wrong. If you drew that first one where there was one mono substituted, there's the word, they would absolutely say you were wrong. And they would say, were there other hydrogens that you could have removed? Hopefully, that would have been the hint. Make sense? And that's all I have. Okay, next.
Question 7, chapter 8.
So, we'll just pretend all that disappeared. We want to run a chemical reaction with this. Should it be substitution or elimination? What do you think?
So we need to see like substrates or whatever.
Substrate? Do we have a substrate? Yeah, that's the substrate.
That's it.
Yeah, that's the substrate. We absolutely see the substrate.
Oh, well, I guess the nucleophile.
Okay, deciding whether we had a strong or a weak nucleophile would allow us to differentiate between 1 and 2. You're right. I didn't give you any of that information.
That's what it is.
Tough. Look at the substrate.
Well, OH is a weak nucleophile.
push on some of your wording there. You said OH is a weak nucleophile. Okay. Is OH a good drawing as I have drawn it?
Yeah. Space it out. Line.
Sure. Oxygen would be missing its octet. We would need to show the lone pairs to get there. And as soon as we did that, what we should also see? A negative charge. OH, as we're referencing, or at least when we're saying OH, is hydroxide. Hydroxide is not a weak nucleophile. It's a strong nucleophile. Okay? If we were talking about the OH connected out to another nonmetal, now you're looking at a weak nucleophile. Okay? So if we take your statement and apply it back to this, you're saying the substrate is not the substrate, you're saying the substrate is the nucleophile. Is that really what you want to say? Okay. So then we're in a whole different scenario. We could say it's a weak nucleophile. We're looking at a one-type mechanism, be it SN1 or E1, and we would need to know what the substrate was that we were reacting with. Okay? I appreciate all of those conclusions. Yes, that's okay, except I said that's the substrate, not the nucleophile. So you switched the question on me, which is okay, your valid interpretation, but now we've moved to an entirely different scenario. That's the substrate.
So is it like testing them out, like, you know, testing out a weak and strong nucleophile?
I don't know what the nucleophile is, so you can't talk about the strength or weakness of the nucleophile because there is none right now. All we're looking at is the substrate and trying to glean as much information out of the substrate as we possibly can. Okay? And this is what you need to be able to do. You need to be able to look at any one of those four components for an individual reaction: substrate, leaving group, nucleophile, and solvent, and interpret that one thing into what it could potentially mean. You have to be working on that skill set. Okay? And if you're trying to pull all of the information down, you may be able to answer that one question, but when I switch to now which of these is the best substrate, you're going to be like, I don't know. What's the nucleophile? I don't care what the nucleophile is. I care what the substrate's telling me. So when we look at this, what does the substrate tell you? What should the substrate have? Let's try that. Say it again. So the substrate should have a leaving group. What would make a leaving group? What does it need to do?
Strong pull of electrons?
It has to pull the electrons away from the carbon. So what must be true about the identity of the leaving group in comparison to the identity of the carbon?
Electrons.
I need the leaving group to have a larger electronegativity than the carbon so that the leaving group can take electrons away from the carbon. So when I now go through and look at this structure, do I see the potential for a leaving group? Yes? Where is it? The hydroxide, okay? And again, we're using hydroxide in a bad context. The hydroxy would be better, but it's still kind of confusing. Again, confusing with the OH. So what you could be saying is your leaving group is this OH. Okay? We've got a potential issue with that. So let's just draw it out. I'm not sure why I'm drawing all of this, but I already did it, so we're stuck there. Okay, this is the thing I want to talk about. Is that a good leaving group? Because for all four of our things, we need a good leaving group. Whether we're SN1, E2, E1, SN2, E2. I need to have a good leaving group. And in all the videos, I go through and say leaving group is ultimately a misleading thing because it has to be good regardless. Okay? Is hydroxide a good leaving group? What makes a good leaving group?
Makes sense compared to the strength too.
True. That's part of it.
Maybe make some consonant.
Okay? If it was neutral when it left, so we could evaluate charge, size, all of those things. Really what we're asking now, which is challenging, is in an absolute sense, is this a good leaving group? So I'm not comparing it to anything else. I'm just saying, is it good enough to leave? Okay? What we're actually establishing is a line. Okay? Hydroxide is a better leaving group than hydride. Why? They both have the same charge. What's next? Size. Is there a difference in size? Yes. What's that difference in size? Well, yeah, it's a lot. Which a lot?
Oxygen,
Oxygen is larger in size. What does that mean about its ability to stabilize the negative charge?
more area to electrons.
Okay, so it can stabilize it better than the hydride. Awesome. So that explains hydroxide being better than hydride. Okay? What we're talking about is in now shifting away from a comparison to an absolute system. Okay? In this comparison, we're effectively saying, which do you rather want to get hit with? A knife or a broadsword? Okay? If I gave you that choice, what's your first kind of gut response?
Well, with the what sword?
Make it any sword you want.
Um,
What was it? Neither. Those are two awful choices. Okay? Yeah, I can try and debate which one's going to allow me to survive better or bleed out less. I don't know. Okay? But your first choice isn't let's decide which of these is better or worse. Your first choice is those both suck. How about you don't hit me with one of those? That's what I'm asking now. Is hydroxide a good leaving group? That's a hard question. That's a big shift from how we've been doing things. Okay? One of the things that contributes to our leaving group ability is that it must be stable. So chlorides, great leaving groups. Why?
stable and strong.
How do you know they're stable? How do you know chloride is stable? Where have you seen chloride before?
Exist in the world.
Yeah, where? Table salt. Do you ingest table salt?
Yeah.
And don't get all poetic on me medicinal stuff. Is that stable?
Yeah.
Yeah, you don't ingest that and be like, oh, I'm dead. You're like, oh, that tasted good. Okay? You had a rough exam. What happened? You cried. What's in your tears? Salt. Is your face melting off? No. I pour hydroxide on you. That was stand further away from you. Okay? That's a bit of a problem. You get hydroxide dumped on you. That's corrosive. That's skin melting, burning, all that nasty stuff. Is that stable? No. What does that mean? It's not a good leaving group. Okay? So the halides are nice to start with. Oh, they're just great. They just, fall right off. Okay? Not all leaving groups just fall right off. There's a line in the sand of what's good and what's bad. Okay? That line isn't always obvious. Hydroxide has crossed that line. It is not a good leaving group. Okay? What would make it a better leaving group? Okay? So we could shift to a slight different definition change, which floats out there. We want a weak base as our leaving group. Which is ultimately going back to stability. Is hydroxide a weak base? By definition, not. Like, that's the definition of a strong base. So it's not a weak base. How do I make hydroxide a weak base? Neutralize the charge. What's the charge it has? Negative. So what should I attach to it? What's the easiest positive thing I could attach to it? Hydrogen. So before I start this whole leaving group process, maybe what I want to do is put in an acid that produces H+, because what is that H+ going to do? It will bond to the hydroxide. When it bonds to the hydroxide, what happens? Neutralizes it is problematic, because all I've shown is a bond now. The electrons from our oxygen are sharing with the hydrogen. What charge should my oxygen be? Positive. I didn't neutralize the charge. I actually made it more charged. Does oxygen want to be positive? No. So what does it do? it steals electrons from a nearby bond. It could pull them from the hydrogens, that just takes us backwards. Instead, it could pull them from the carbon. Now what happens? We get that whole structure, but now I get H2O as my leaving group. Is that a weak base? Yeah, said another way, is that a good leaving group? Yes. Okay? So one of the things that we have to kind of keep in mind when we run these reactions is that we still need to have achieved a good leaving group to allow the reaction to occur. That OH functionality, as we'll continue to find throughout the semester, is very, very tricky because it has electrons, which means it can act as a nucleophile. True. It could also act as a base. It also has a hydrogen connected to it, which means the hydrogen could be removed, so it's acting as an acid. It also has a carbon connected to it, so the oxygen could take electrons from the carbon, making the carbon a good electrophile. So the alcohol functional group, just looking at that substrate, gives you access to all 4 potential chemical reactivities. Sucks. We want to limit those somehow. Okay? Or provide an emphasis so that I get one direction in preference. Kind of, sort of? Okay. So what I wanted to do was to push on this reagent, look at that starting material, try and decide what's going on with it. We do see the OH as a potential leaving group. It was a bad leaving group. We decided it would make sense to add an acid to make it into a good leaving group. Great. We still need to evaluate our substrate. What kind of substrate is it? And in that question, what you're trying to do is to look where the leaving group is located. Now, I don't care that it's an OH. I just care that eventually I can get a leaving group there. And I want to know that carbon. I want to classify that red carbon. How do I classify it? How many other carbons are connected to it? 2. So when I say classify it, what am I asking for? I'm saying it's a secondary substrate. And I want that flow through with my substrate classification, because if I know it's tertiary, I know certain mechanisms are favored. If it's primary, I know certain mechanisms are favored. If it's secondary, I know all hell broke loose and all mechanisms are possible. Does that make sense? So I want you to look for those pieces, because those pieces can allow you to expose yourself to different channels of reactivity. Okay? And if we do that, we recognize with a secondary substrate, we've got a big problem. We would need a lot more context to help narrow the field. Okay? This is where we delete everything and go back and look at what the question asked. The question says specifically we want to go through an SN1, and the reagent we're adding is HBr. If we were going to do SN1, we're doing a substitution with N being nucleophile, which means the reagent needs to supply what? Electrons. And if we look at HBr, what does HBr supply? When you think about the reactivity of HBr, you think about Br minus? You think about H plus, because HBr is a strong acid that's like melt your skin off kind of a problem. So that seems a little bit weird. Why would I want to add an acid when I'm looking for a nucleophile? What's the point of the acid? What was the point of the acid? To set me up with a good leaving group. Once I formed that good leaving group, I now have the potential for it to leave the structure. Once it leaves the structure, I've now formed what? A carbocation. Why did I want to form a carbocation? Because it was an SN1 pathway. That information can come secondary if you follow the chemistry. If you choose to not follow the chemistry, you have to follow it more abruptly with what's specified within it. So if we're looking at this, our SN1 reaction required an acid-base reaction to start. Then it moved into the SN1 pathway with the next part, and the first step of our SN1 is heterolysis. Okay? Now we could look at the other product, and the other product, we also have Br minus. That's cool. What did I want in the SN1 or SN1 pathway? We already have a carbocation. What do I need next? SN1 pathway. Nucleophile. What else do I have floating around? Presence of that nucleophile could now potentially come in and react. Why would it come in and react? Say again? Sorry. Positives and negatives. Okay? That positive is unstable. I want to stabilize it by giving it electrons first. Okay? When you do the homework, what's the first thing you do? Okay, read the directions, then what?
The homework.
Oh, you just do the homework, right? What happens when you get it wrong?
Try again, look at something else, try a different method.
Try again. Okay, then what do you do? You're still wrong. What do you do? Try again. Then what do you do? What's that? Okay, you should have drawn it out the first time, so we'll sidestep that. You're still wrong. Then what do you do?
Ask you.
Wait, so you focus internally on what you know first before you reach out for help?
Yes.
Guess what chemistry does? Same thing. I've got a carbocation. The problem is it's missing electrons. Before it reaches out for help, it wants to look internally first. Are there other electrons internally?
But they're all connected.
They are all connected. Was that a problem if we were going to do an elimination reaction, if I added a strong base, right? What does that strong base do? Because the strong base doesn't react with that positive, does it? The answer is no. Bases don't react with carbon positives. What do bases react with? Okay, so go home, rewatch the video, rewind back. We're at what, 68 minutes right now? Go back to probably 55 minutes. Okay, and at 55 minutes, we literally talk about what the base does. What does the base do?
Gives electrons.
To what? Because if I'm going to say this is a base and it gives electrons to that carbon positive, that's not a base, that's a nucleophile. What do bases give electrons to? Define a base. A proton acceptor. What is it donating the electrons to? A proton. What is a symbol for a proton? H plus. Where must the H be if I was going to do an elimination reaction?
Loading.
It needs to be one carbon away from my carbocation. It needs to be at the beta position. And if I look at the beta position, are there hydrogens there?
Yeah.
Ooh, there are indeed. So my base could come in and remove the hydrogen and do what with the electrons in that bond? Make the double bond. So were there electrons already within this structure? Yeah. So the structure doesn't have to look out to a nucleophile. But Mike, then you're telling me it looks out to a base. That's true. Get rid of the base. Do I still have electrons in that bond to the hydrogen? Yeah. So how about we take the electrons in that bond and we move them over here? What happens?
Lose hydrogen.
Do I lose the hydrogen? It's an interesting question.
Oh no, maybe, I guess.
Okay? I'm taking the electrons in that bond and I'm putting those electrons, instead of in the space right here, I'm now putting them in the space over here. Right? So it's no longer here.
Right.
It's in that other space. What did that do to the positive charge?
Neutralized it, but now.
Ooh, it neutralized it. The but now is an awesome statement. I like that. We'll come back to that. The positive charge on our carbon is no longer there because we took those two electrons and we put them over here. So now that carbon has lost its positive charge. Absolutely 100%. It's no longer positive. It's gained electrons. It's now neutral. But what happened to the original carbon where our hydrogen was? It lost electrons. Therefore, it is positively charged. I want to get rid of those dotted lines. It's killing me. It's now positively charged. What happened to the dashed methyl? It's still there. Is it still dashed? No, why not? It's not chiral anymore because it lost that fourth bond. Okay, which means solid line to my methyl. Okay? Well, why would it do that? Why was this unstable? For the record, we're pointing at our purple carbocation. Why is our purple carbocation unstable?
It's got a charge.
Okay, well, so does the blue one. Is there a difference in stability between them?
Yeah, because isn't there like the electrons around it?
Yeah, if we look at the electrons around it, we're looking at the purple one as a secondary carbocation, whereas the blue one is tertiary. Which one's more stable? The tertiary carbocation, which means this is a favorable reaction to run. What we just did here is what's known as a rearrangement. Rearrangements suck. I mean, well, they're really cool, but at the same time, they're very painful to deal with. Okay? Rearrangements are looking for the answer within the molecule before it reaches out. How often does that happen? Enough to be obnoxious. Okay? You won't see rearrangements in an SN2 reaction. Why not? It's all happening at once. All of that chemistry is going whoop all at once. Why do we see it in the SN1? It has time to do it. Why does it have time to do it? What does it produce? When we say one type, we say carbocations. When should you be concerned about rearrangements? The instant you see a carbocation. As soon as you see a carbocation, you go, damn, I got to worry about a rearrangement. Look for the rearrangement. There's a variety of ways that rearrangement can happen. We can move hydrides. They're hydrides, not hydrogens, because we're moving electrons. Okay? You can move carbons. Okay? They will invariably be immediately next door to make that shift. Okay? There's all sorts of rearrangements out there. You get lots of named types of rearrangements. Okay? Focus on it stabilizing your intermediate. Okay? So we're transitioning from a secondary to a tertiary. Can I do another rearrangement? Isn't there another hydrogen over here? Couldn't I have moved that blue hydrogen? Say again? If I did that rearrangement, what would I result in? Another tertiary carbocation. Is the tertiary carbocation more stable than the tertiary carbocation? They're the same, which means it doesn't happen. Your rearrangement only happens when it makes a more stable product. So you can get tertiary transition or secondary transitioning to tertiary. You'll never get tertiary going to tertiary because same stability. Could you get tertiary transitioning to primary? Misleading question for the record.
Could it happen with a carboanion?
It can. Our focus is primarily carbocations. It's a different system with anions. Can a tertiary ever transition to a primary? Your statement, bold statement, I like it. No, because primary is less stable than tertiary, right? What if it's primary with resonance? Does the resonance stabilize? Yeah. So you could get a sequence of multiple rearrangements. Typically, you're only looking relatively short, just one hops. But you can do a whole bunch, depending on your structure. So this gets us to our carbocation. Does this get us to our final answer? No, because what are they asking for? They want the products of this reaction. Interestingly, they say 2. Why do they say 2?
There's two possibilities.
Why are there 2 possibilities?
Bunch of hydrogens.
SN1 forms what? Carbocation. Where's the carbocation? Generally, where is a carbocation housed on an individual carbon? I know it's a hard question. It's in a p orbital. Where's a p orbital? Above and below, which means where can my nucleophile come in? From above or below, which means 2 potential products. Okay? Particularly if I had chirality to start with. Do I have chirality to start with? Yep. Which means the relationship between those products is not identical, they're diastereomers. Most people will go through and draw the carbocation here in purple, and then draw the product with our bromide coming in and tacking above and below. And they get it wrong, and they can't figure out why. It's because what they missed was the rearrangement. As soon as you do the rearrangement, now do above and below. You will still have 2 chiral centers. You've got to make sure you've got those locked down. This was a question you asked. In the interest of time, since I'm now way over, I will be somewhat kind for those in attendance.